Okay, welcome to the Math216 lecture recordings. This first recording, the purpose is to try to communicate the level of expectation in this course. And broadly speaking, we're going to expect you to understand the ideas at a deep level and to be able to apply the ideas in previously unseen situations. So now, what does that mean, though? So the purpose of this lecture is to give you an example of what kind of, what do I mean by understanding things at a deeper level, and what kinds of unseen previous examples might we be talking about. So there's a particular little math problem that I want to talk about here. Now, the actual math of this example is not the point. The math in this example is cute and clever and creative, but not really Math216 material. The math in this example is just serving as an example, a template on which we can talk about what I really want to talk about, which are what does it mean to understand something deeply, and what are creative applications. So here's the little math problem. So we'll start off by considering an 8 by 8 array of squares, such as this right here. And imagine that we have a collection of 2 by 1 tiles, such as that we're allowed to place on the array like this. And if you want to think of these as being dominoes that you're placing on a checkerboard, then that'd be just fine. Okay. So now obviously there are 64 squares on the array, and each one of these tiles covers 2 squares, and so doing the arithmetic, if you have 32 of these, clearly that will cover the array. Now, at least from an area standpoint, the area is sufficient. Now, how do you actually do that? Well, you just do it like this. All right, so it's not hard to see that you can actually cover the entire checkerboard with the dominoes. Okay, but now here's where it gets interesting. What if you were to cut off 2 opposite corners? And furthermore, we were to remove one of the dominoes, one of the tiles. Now, from an area standpoint, it remains that it seems like it ought to work. We have an area of 62 that needs to be covered with 31 tiles, each of which has area 2, and so you'd think that, again, feels like it ought to work. So here's the question: can you actually do it? Well, here's what you'd try. You'd start off by laying down the dominoes in a natural way. Now, we've sort of created a corner here. There's only one choice. I really have to do that at this point. And then I realize, oh, well, then I really have to do that at this point. And that's here. Now you get to start making choices. Let me try this. Let me do that, and then that, and then that, and then this, and then this, and then that, and oh, now I've got to do that. Seems like maybe we ought to do something like this, and I could do that, but that's a bad idea. And then look, I've painted myself into a corner. I can't get that square, so let's do this, etc. You can proceed along and try to make a guess as to how you might do this. And what you will find is that despite your best efforts to avoid it, you will paint yourself into a corner. So your first attempt is going to fail. So you try something different. Maybe you do that, right? And then something like this, maybe. Okay, maybe that will, maybe we'll do that. That's a different thing, and maybe we'll go off in this direction, etc. That's going to fail as well. You keep trying things, and you will keep failing. Okay, so our own personal failure doesn't mean it's not possible. It might be that there's some way to cover this, and we just have not yet happened to have found it by our aimless, random attempts. Or it's also possible that, this can't be done. How do we tell the difference? So it remains, we don't know the answer to this question. Can this be done? Can 31 tiles cover this array? Okay, well now you could conceivably program a computer to do this. Right? Think about all the different possibilities. Each domino covers two squares that one could assign coordinates, and you could think about how you could keep track of this, and let the computer try it billions of times. Okay, but for one thing, there are billions of attempts that would have to be tried. A computer can handle that. But the asterisk, we'll come back to that in a minute and see how that's not actually a very satisfying answer. But even if the computer can answer it, did we really learn anything by having the computer doing a enormous amount of trial and error for us? And, well, no. Okay, so here's a clever solution. I like to call this a creative solution. I'll come back to that in a moment. And you remember we referred to this array as a checkerboard. You can think of it as a checkerboard, dominoes covering a checkerboard. Well, let's now deliberately think of it as a checkerboard. Let's apply a checkerboard pattern and, color in with black and white. Let's color in every sort of other, diagonally connected square in this way. Standard checkerboard pattern. Okay. And notice that every tile, however you place it down, is going to cover not only two squares, but specifically it's going to cover one black square and one white square. Always. Whether you do it that way, or whether you lay down the domino like this, or like that. Every single way that you lay down the domino, it always covers exactly one black and exactly one white. So now I'm going to define this number called I, and I'm going to say however it is that you've placed down your dominoes, I is the number of black squares that you've covered with your dominoes minus the number of white squares that you've covered. And keeping in mind that every domino covers exactly one of each, it follows that this number I is always 0. Okay. All right, so what? Well, here's the thing. Keep in mind we've removed this square and that square. And keeping in mind how the diagonal checkerboard pattern works, you see that those two squares are the same color. Now, I don't know if they're going to be both black or both white. Depends on how I define the checkerboard pattern, but they are certainly going to both be the same. Now, the way I've done it here, that's white, so they would both be white. Doesn't matter. The point is, either way I do the checkerboard pattern, there will be different numbers of black and white squares. So a hypothetical covering that covered all of the black squares and all of the white squares, if there were more black squares than white squares, then this number I would have to be non-zero. Right? The I number would have to be 2 or -2, depending again on whether what color were these two squares that I removed. Well, this isn't possible, right? It is not possible for I to be 0, as it clearly must be, and to also be either 2 or -2. So that's a contradiction. So what that means is this hypothetical scenario where I have covered all of these 62 squares with these 31 dominoes, that hypothetical scenario is not possible. Leads to a contradiction. So we didn't have to try billions of trials, right? This clever solution of thinking about the checkerboard pattern and thinking about this number I and what it must be allows us to come up with an answer with no tedium at all. Okay, so I like to make the observation at this time, this is a truly creative solution. And I mean that in a very literal sense. The word creative does not mean, it's not synonymous with artistic, right? Creative just means that we have created something. And the pattern we created that checkerboard pattern in this problem. The problem was not given. Excuse me, the checkerboard pattern was not given in the statement of the question. We made a choice to impose that. Our free will, we decided to color the squares with that pattern. Likewise, we created this number I, right, this formula here, B minus W. We made that up. That was not given in the statement of the question. So this is very literally a creative solution to the problem. And I think it's important that students understand that this is very much how math works. Math is full of creativity. We create different kinds of structures depending on the nature of the problem. We come up with structures that are appropriate to the problem that help us solve the problem. Okay. I also think it's a good little bit of math culture to note that this number I that we defined up there is an example of something that is also common in math. It's an example of a powerful mathematical strategy called an invariant. So the idea of an invariant, you look up here to our scenario, is it's something that doesn't change even though it's computed from something that can change. So here, this invariant I is computed from any possible arrangement of dominoes, and even though there are billions of different possible arrangements of dominoes, right, however you might lay out the dominoes, all these different possible arrangements of dominoes, each arrangement gives you the same value of this number I. So this number I is an invariant. Understanding, creating and understanding invariants is a powerful strategy in math. And so be on the lookout for that as you move on through your math studies. Okay, so now what we've finished now is this is, you might imagine, a little lecture that you would view in this course or a future math course. And now that I've given you the little mini lecture, I want to show you some examples of what we mean, or what is the level of expectation. To what degree would I expect you to understand this discussion here? What might test questions look like, and what might homework exercises look like? So, what in this context of what sort of do you need to know? So here are several questions that might come up. For example, if this were Math 216 material, which, let me emphasize, it's not really the point of this problem. Okay, so here's a really easy question. The question on the exam might say, suppose you have an 8 by 8 array. Suppose you remove opposite corners. Is it possible to cover that with 31 dominoes? Well, that's an easy question. In fact, that is exactly the question that we just discussed. So if this question were to come up on an exam, that's just testing whether you actually remember what got discussed in class or in the recorded lectures. So that's an easy question. Now, this is something that we do expect. We do expect you to remember these specific applications, the specific methods that exactly as done in class. Sure, of course. But I want to emphasize that's not all that we expect, right? So there are higher levels that we want you to understand the material. So, for example, let's consider this. There might be an exam question that says, suppose you have a 20 by 20 array. And suppose that opposite corners are removed. Can that be covered with an appropriate number of dominoes? Well, that's not the same question. Right? It's a significantly different, quite much bigger array. But if you understand the idea behind this, the solution to this problem, you can see how to adapt it appropriately to come up with a solution to this problem. In fact, everything that we did goes through. So, for example, in a 20 by 20 array, can I cover that with a checkerboard pattern? Sure, no problem. Right? If I remove opposite corners, are those corners the same color? Well, now you've got to draw yourself a little 20 by 20 checkerboard pattern, and there's the opposite corners. And you have to think about the arithmetic involved. That's 20, that's 20, and go through, and it's not hard to persuade yourself that, yeah, that's the same color as that. Okay. And then think through, all right, how do we define the invariant, and do we get a contradiction? And in fact, you do. It's not hard to go through the little details and confirm it. Sure enough, a very, very similar argument works. This pretty much morally equivalent argument there also works here. And in fact, not hard to persuade yourself, it works here as well. So by the way, this shows already the fact that we can answer this question about a hypothetical 750 by 750 checkerboard. Actually shows one of the reasons that this strategy, the program it into a computer and have the computer do the work, is also unsatisfying. Because with 8 by 8, there are already billions of different trials that you would have to try if you wanted to use process of elimination. With 750 by 750, staggering to imagine how many different trials, how many different ways could all of those dominoes be arranged. And the number is so large that there's no way that a computer could do that many computations. 750 doesn't sound like a big number, but you got to think about how many dominoes are required in 750 by 750, and it's immense. It's hundreds of thousands of dominoes, a couple 100,000 dominoes, and each one of which can be arranged in 2 different ways. So ballpark, we're talking about 2 to the power of a couple 100,000, and that's a tremendously large number. And again, no computer couldn't even consider it. So coming up with a creative solution gives us capabilities that we could not do on the computer. You can do this on the computer. You could not do that on a computer. Okay. At least not by brute force. Okay, now next question. What if it were 10 by 20? Now here you've got to be careful. Now we don't have a square thing. It's not immediately clear that these 2 squares are the same color. Right? You can't just draw a diagonal there because that's not the square we're actually interested in. So you've got to think about now, how would I persuade myself one way or the other as to whether these are the same color? And one way that you can do this is keep track of what you might call the coordinates. Come up with I and J that indicate, which column are you in and which row are you in. And notice that 2 squares are the same color if I plus J has the same parity. So if I plus J for 2 different squares are both even or both odd, then they're the same color. And think it through and think through the 2 different corners, and you can persuade yourself that, in fact, yes, the 2 corners are the same color. So point is, eventually it becomes the case that the same argument will apply. But there's more work to be done here. So to answer this question, we had to adapt from the method that we talked about in class more. And as a student, you've got to be prepared for that possibility that it might not be an immediate, like these, immediate application of the ideas in class. There might be more adaptations that are necessary, such as in these cases. All right, what if it's 75 by 150? Well, it's tempting to lump these all together and say, well, these are all similar, right? They're both sort of not squares, or sort of 1 by 2-ish shaped rectangles, and so, yeah, same idea. But the devil's in the details. This is something that students can check for themselves, but in fact, in this case, when you make your rectangle, this square is not the same color as that square. They are opposite colors. So the argument fails. The point is that this invariant that we define, this invariant is B minus W. Well, I'm doing green and purple here, but white doesn't show up well in the white background, so let me do green and purple. In fact, I'll say, green minus purple the invariant's always 0. But a hypothetical scenario that covers this, because I've removed 2 squares of different colors, the hypothetical coverage would require the invariant to be 0, which it is. So there's no contradiction. So we can't. This doesn't. Our invariant argument doesn't disprove anything. So the argument fails. Now that makes this a very significantly different question. If this question were on the exam, right? This question would require students to identify what it is that went wrong and to then take the appropriate action and realize that the student would then have to approach the problem in a totally different way. In fact, not only do you have to take a totally different approach to the problem, but in fact even the answer changes. In this case, you can actually cover it. This can be covered. You can do something like this. And then the remaining in here can be covered like that. And, etc. So not only does the method not apply, not only do you have to approach with a different method, but you get a different answer. So you got to be on the lookout for that. So you'll notice the rising level of expectation as we go through here. This is just memorization. That's easy. Here, there's a little bit of an adaptation that's needed. Here, there's more of an adaptation that's needed. And then increasingly, these problems are becoming more and more different from the original, what was actually directly given to the students in class. So there's lots of different variations. You might consider, by the way, what if you have 100 by 100? Non-opposite corners are removed. Well, again, that's a different question. You got to think through, does the argument still work? The devil is in the details. So think through the details of the argument and ask yourself, and this would be a good exercise for students to do on their own, does the argument work? Or does it not? Likewise, now the problem at this point is this is actually quite a difficult problem. What if instead of corners, just 2 unspecified squares of different color? Now, if they were the same color, the invariant argument would clearly show a contradiction, therefore can't be covered. But if they're the different colors, the invariant argument fails. How would you address this question? This is, again, a very challenging question. And then also even more challenging, really, is what if it's 300 by 300, but the tiles are now no longer regular dominoes. Now the tiles are 3 by 1, and we remove 3 corners. This requires some very significantly creative solution. In fact, to answer this question here, you have to create something that we did not previously discuss. So this type of a question shows this would demand a level of comprehension at a very deep level. Namely, you'd have to see how it is that the checkerboard pattern was helpful and come up with your own creative new pattern to impose on the array that would serve a similar role for this different situation with 3 by 1 dominoes instead of 2 by 1 dominoes. So that's a hard one. Something to think through. Okay, so the point again to this is not to teach you about checkerboard patterns and dominoes and this kind of thing. The point to this is to communicate, what is expected in Math 216. If you are accustomed to taking math classes where you pretty much only have to, be able to reproduce what you were shown, well, it's going to be very different in Math 216. If you are accustomed to reproducing what you were shown and maybe making just, simple adaptations, maybe a little bit more. But, still everything kind of working out the same ways that you've been shown. Be prepared. Math 216 is not going to be that direct. It's not going to be that immediate. So you have to be prepared for reproducing what you've been shown, easy adaptations of what you've been shown, and how to be on the lookout for problems that are significantly different, possibly even very challenging problems that are significantly different from what you've seen in class. And all of these types of questions serve the purpose of testing to what extent does the student understand the ideas, the fundamental ideas on a very deep level, and to what extent can the student take that understanding, that deep understanding, and use it to solve problems that you have not yet been shown how to do. Okay, all right, well that ends our first recording.